Hi again, Paimarads. Welcome to the second part of the economic exercise about demand for lemonade. In the first part, we managed, based on the given demand curve, calculate the optimal price to maximize our profit from selling 100 lemonades. Every business, of course, craves the knowledge of the demand curve because it optimizes their money making. And for some types of service, revealed preferences, your past spendings, or even auctions serve the purpose of measuring so-called willingness to pay, WTP, which is basically the demand curve. Now, we are going to consider one particular example for a demand curve, and that's when scientists Lasker and Schroeder managed to measure demand for American steaks in 2004. They had two groups of volunteers, which were asked the same set of questions about their steak preferences. First group, based on their answers, had to purchase their favorite steak, and that demand we will denote as non-hypothetical, because they had to spend money. Other group, which had to answer the same set of questions but didn't have to buy the steak in the end, is denoted as hypothetical. Now, for the purpose of this exercise, I have digitized their published curves from the study. They consist of x values, which is basically the price axis, and there are 7 in total, and corresponding hypothetical and non-hypothetical demand values, 7 of each. Because we have so little experimental points, we are going to interpolate them. Essentially, we want to connect the given points with a smooth line and claim that true function behaves similarly to that. Related term to interpolation is extrapolation, which is estimating the functional values outside of the interval of the given data. Therefore, extrapolation is much more dangerous and error-prone, somewhat like predicting future. Okay, now, how do we execute the interpolation? After the import of the interpolate module from the SciPy package, first thing is to define our new x values. So the values of price for which we want to learn the demand. I have linearly spaced them between the edges of the x interval from above, and I have created 201 values. Next is to apply the interpolation method on my original data. I use function interp1d, one-dimensional interpolation. Original data is x and data hypothetical or non-hypothetical, and I use so-called cubic spline, method cubic. Not important to understand, but it is, trust me, the most simple and commonly used. This returns a function, so f hypothetical or f non-hypothetical. In order to get the demand values, I need to apply this function to an independent variable, which is in our case the newly defined price axis. In this way, I will get 201 demand values for both hypothetical and non-hypothetical demands. We can run the cell. To plot the data, we are going to use our well-known PLT plot function. It takes the x values of the original data, that was x, and data hypothetical. They are just 7 points, so we are going to plot them red and circle, and we create also a label for them, and that was called study hypothetical, let's say. For the second data set was sharing the x-axis, but data were called data Nonhype. We are going to use green markers, and label will be study non-hypothetical. Next is to plot the interpolated data. So that's on the new x-axis, which had these 201 points. So that's price new. The y values were called demand, and again hypothetical. Let's plot it in black. That is a line, so no marker. And label is going to be interpolated. Second set, PLT plot, same x values, y values are now non-hypothetical, again is going to be in black, and we don't need a label. We run the cell, and first what we see is that the interpolation works, because it reasonably connects the experimental data with the smooth function. Second, notice that the hypothetical demand, in red, is always higher than non-hypothetical. People are less positive about the stakes if they need to buy it in the end. And more wavy demand curves also make sense. At low prices, the demand flattens because everyone who wants a stake will be able to afford it. The flattening also appears at the high end for the prices because there will be always rich enough people, no matter what the price, if they feel like having a stake, they will simply buy it. Now, the question is, when we apply these two curves to our lemonade, are we going to earn more or less money? The procedure will be the same as before, but you can already guess that since these curves are not known functions, the profit will also not translate into quadratic function. Therefore, it is impossible to solve this on paper. But in Python, we are going to do exactly the same as before. First thing is to calculate demand for 100 lemonades. So that's 100 times demand. And one is hypothetical, and the non-hypothetical is exactly the same. Demand, non-hype. Profit, we calculate the same, so that was the price we set times the demand. So price is now price new times demand hypothetical and for 100 lemonades. Second one is exactly the same, price new times demand, and now non-hypothetical and 100 lemonades. Expenses are the same as above, so we don't need to recalculate them. And profit will be, again, income, and now hypothetical minus, it was called total expense, and income non-hypothetical here, and the expense is the same, so total expense. Since we have now calculated the profit for hypothetical and non-hypothetical demand curves, we can plot all three curves together. So first is the original one, PLT plot, was on the axis price, and we have called it simply profit. We add the label again, not to confuse things. Let's say profit. Now second curve, same function, PLT plot. We have new price axis, price new, and we have profit, let's say hypothetical. And we add corresponding label, which will be profit hype. Third one, PLT plot, price new, profit non-hypothetical, label profit non-hype. As I have warned you already before, the profit curves are not the quadratic functions anymore. However, we can still find lemonade prices which lead to the maximum profit. For the orange curve, we can actually earn more money than with the original linear demand curve, and even at lower price of the lemonade. However, once people actually need to buy it, our profits drop, and unfortunately they drop below zero. Now we are going to use a print statement in the form of so-called formatted string, where we can combine strings with variables in order to print the maximum profit from the profit array and the optimal price for one lemonade, which is from the new price array, and we need the argument of maximum of the profit array as the indexing part. Once we run the cell, we learn that our hypothetical maximum profit is 137 money, which is more than in the first part we got 500, and the lemonade price should be 37 money. For the non-hypothetical group, we do the same, and we learn, unfortunately, that our maximum profit can be minus 34 at even lower price of the lemonade. The most important message, therefore, is that asking people about the willingness of spending money and their actually spendings are two totally different things, and that can make a difference between flourishing and bankrupting businesses. In the end, I have a question for you to further improve the notebook. So can you modify it in order to use the minimize function from the optimize module in order to find the maximum profit of the theoretical linearly decreasing demand? Good luck with that, good job so far, and see you at some other exercises. Cheers!